This is a revised presentation of Quantum Condensation and Un-Condensation, aligned with the updated paper defining information as physical records in matter and fields, rather than abstract or observer-based notions.
It's great to be here, and honestly, that opening statement it's really the only way you can start this conversation. It puts the whole thing in frame right from the get-go.
It really does.
Oh.
Welcome back, everyone, to the Deep Dive. We have a stack of research in front of us today that tackles what might be one of the most fundamentally mind-bending topics we've ever touched on.
And that's saying something.
It is. It is. I know I say that a lot, but this time it's literal. We're talking about the physics of reality itself. We're diving into the work of Lev Motin, PhD, and specifically his paper, Quantum Condensation and the Physics of Information Reversal.
Yeah, and you should know right away, this is not your standard quantum mechanics lecture. This isn't just, electrons can be in two places at once. It's a proposal for a whole new way to look at the solid world around you.
Exactly. We're standing right at the boundary, the line between quantum possibility, the fuzzy, weird, probabilistic stuff, and classical reality, the hard, definite stuff.
The chair you're sitting on.
Right. And we all kind of know the story. Things are wave-like, they're possibilities, and then something happens, an observation or whatever, and they become solid. They become a fact. But the question we're asking today, the one that usually gets you some funny looks, is, can we cross back?
Can you take that solid thing, that fact, and dissolve it, turn it back into the fuzziness?
Can you unhappen a fact? That's the big hook. But to even begin to get our heads around that, we have to start with the core analogy in Motin's paper. It's so good, and it really lets you see the physics without getting bogged down in the math. He talks about vapor and droplets.
It's a brilliant metaphor, and it's essential we stick with it for this whole conversation. He argues that quantum states, all those superpositions, the spread-out possibilities that make your head hurt, they're like vapor.
Okay, like steam.
Exactly, like steam. It's diffuse, it's kind of everywhere at once in a container, it flows, it has a coherence, all the water molecules are part of the same collective thing.
It's the ghost in the machine.
That's a good way to put it. And then classical reality, the facts, the chair I'm sitting on, the coffee mug in my hand, those are the droplets.
Localized.
Yeah.
Definite, concrete.
Right, and that transition, which physics textbooks often call the collapse of the wave function, which sounds so, I don't know, dramatic and violent.
Like something breaking.
Yeah. He just calls it condensation. It's no more magical than water vapor condensing on a cold glass and forming a bead of water.
I love that image because it immediately takes the spooky, mystical element out of it. Right. It's not magic. It's a phase change. It's just gas turning into liquid.
That's the whole point.
Yeah.
It's a physical process, not a philosophical one.
So that sets up the mission for this deep dive. We think we understand, more or less, how vapor becomes a droplet. That's the forward arrow of time. That's cause and effect. That's history being written. But today, we're asking, can you heat the droplet? Can you boil it and turn it back into vapor? Can you take a concrete event that has already happened and uncondense it back into pure, unwritten possibility?
The ultimate control-Z on reality. But, and this is a huge part, but to even understand if that's possible, we have to totally rewire how we define the word information. And I mean, completely throw out the everyday definition.
Let's do that right now then. This is our section 1, redefining information. And I'll be honest, this was the part of the paper where I had to stop, put it down, and just sort of stare at the wall for a few minutes.
Because it's the linchpin for the entire argument. If you don't get this piece, none of the rest of it makes sense. It just sounds like science fiction.
Okay, so let's unpack it. Most of us, and I'm definitely including myself in this, think of information as an abstract thing.
Sure.
It's symbols on a page, right? It's bits, ones, and zeros in a computer. It's numbers in a notebook. Or it's me knowing something. Like, I have the information that the traffic light is red. It feels like mental stuff, something in my head.
And that is the exact misconception that Motin's work directly attacks. He argues that, from the universe's perspective, if information is just some abstract thought in a human brain, then physics doesn't care about it. Physics cares about mass and energy and momentum.
Physical things.
Physical things. So in this paper, information is strictly 100% physical. It is not a concept. It's a thing.
Okay, so help me visualize that. When the paper says information is physical, what does that look like? What am I picturing?
You're picturing an irreversible physical change in matter and fields. It's not a thought. Motin basically calls it a scar on the universe.
A scar. Wow, that's evocative. But I need concrete examples. If I'm not writing in a notebook what is a physical record, let's take a simple event. A single quantum particle hits a wall. in my mind, okay, it bounces off. Story over.
Right. To you and me, on our scale, nothing really happened. But if you zoom in way down to the atomic level, it's a car crash. When that particle hits the wall, it physically shoves some of the wall's atoms out of their nice, neat, comfortable lattice positions. That's a displacement. That is a physical change.
So we've got a little microscopic fender bender, a dent.
A dent, exactly. But it doesn't stop there. That collision creates heat. And in physics terms, that's a thermal gradient. A little cluster of atoms is now vibrating way faster than all of its neighbors.
Right, it's a hotspot.
It's a tiny hotspot. And that impact, it also sends these little shock waves rippling through the solid structure of the wall. Those are called excited phonon modes.
Okay, hold on. Phonon modes. That sounds like some pretty intense jargon. Can you break that down for me?
Of course. Think of a bell, a big church bell. You strike it with a hammer and it rings, right? The sound is just the vibration traveling through the metal.
Yeah.
The wall does the same thing. When the particle hits it, the wall rings with that vibrational energy. The ringing might be too high-pitched for us to hear, but it's physically there. That ringing is a physical record of the impact.
So even after the particle has bounced off and is long gone, the wall is still vibrating. The sound of the crash is still trapped inside it.
Precisely. And until that vibration completely dies down, or more accurately, until we could theoretically track down every single ripple of that vibration and start it, the record exists. The universe knows the particle hit the wall because the wall is, in a very real sense, still screaming about it.
That is absolutely wild. The paper also lists scattered photons and altered electronic states. What about those?
Well, light is always bouncing off everything, right? So photons bounce off the impact site, and their direction and energy are changed. Those are the scattered photons. They fly off into the room carrying the news of what happened.
They're like little witnesses escaping the scene of the crime.
Perfect analogy. And within the atoms themselves, an electron might get knocked into a higher energy orbit. That's an altered electronic state. The atom is physically reconfigured.
So what you're saying is that every single time anything happens, no matter how small, it leaves this huge debris field of physical changes.
Exactly. It redistributes energy and momentum. The universe is physically, measurably different than it was a microsecond ago.
So the big takeaway here, the thing we have to hold on to, is that to say information exists just means the universe has been physically changed.
Yes. There's a line in the paper I have to quote here. Moten writes, "Information is not something stored about a system. It is something done to the universe by the system."
Wow. Read that again. That's powerful.
Information is not something stored about a system. It is something done to the universe by the system.
It's done to the universe. That flips the whole concept on its head. And it connects directly to this crazy idea of reversal. Because now if I want to undo an event, I can't just forget it. I can't just decide I don't know it anymore.
Right. Think about your computer for a second. You drag a file to the trash. You empty the trash. Is that information actually gone?
Well, my operating system tells me it's gone. The space is free.
The operating system says the address is available to be overwritten, but the actual magnetic orientation of the particles on the hard disk platter might still be there. But go even deeper than that.
Okay.
Think about the heat. When your hard drive wrote that file in the first place, the motor spun up. It used electricity. It generated waste heat. That heat radiated out into your room.
Right.
It warmed up the air molecules around your computer, which then drifted out the window, bumped into other molecules.
Oh, wow. Okay, so you're saying the record of me saving that Word document is actually in some tiny way written into the airflow of my entire neighborhood.
In a very real physical sense, yes.
Yeah.
So to truly physically erase the creation of that file, you don't just need to wipe the magnetic bits. You have to go out and catch all those specific air molecules. You have to suck the heat back out of them and put it back into your drive. You have to undo the entire physical footprint.
That makes it clear why forgetting isn't enough. The universe remembers even if I don't.
Precisely. The universe keeps all the receipts.
Okay, so that's a huge concept, but I think we have it. A record is a physical dent in the cosmos. With that in mind, let's do a quick recap of Section 2. Quantum condensation. This is the forward process. This is the vapor turning into the droplet.
Right. We have to establish the baseline so we know exactly what it is we're trying to reverse. So the quantum condensation theory, it pushes back hard against that old mystical view that a conscious observation collapses the wave function.
You mean the idea that my consciousness, me looking at it, somehow forces the universe to make a choice?
Yeah.
Which I have to say has always felt a little, I don't know, self-important to me. Does the universe really care that much if I'm looking at it?
Nemoten's answer is a firm no. Forget magic, forget consciousness. It's a phase change. And it happens in 3 basic steps. First, you have interaction. The quantum system touches the environment.
The steam touches the cold glass.
Perfect. Second, amplification. The microscopic differences, like did the particle go left or right, get blown up into macroscopic distinctions. A single electron hitting a detector can trigger an avalanche of millions of other electrons.
So a tiny whisper becomes a deafening shout.
A shout that the whole environment can hear. And that leads to the third and most critical step, record creation. That durable, physical record we just spent all that time defining is formed.
The dent is made, the bell is rung, the photons have scattered.
And once that happens, the droplet has formed. The event is now a fact.
Okay, but the paper makes another really key point here about stability. Why does the droplet stay a droplet? Why doesn't my chair suddenly dissolve back into a probability wave the moment I turn my back on it?
It's because the environment is constantly reinforcing it. It's not a one-and-done event. The air molecules in this room are constantly bumping into your chair. The light from the ceiling is constantly bouncing off it. The floor is constantly pushing up on it.
So it's being continuously measured.
Exactly. The environment is continuously re-recording its position and its existence over and over and over, trillions of times a second.
This helps me understand that term decoherence.
Yeah.
It's a word you hear thrown around all the time in these discussions.
Mm-hmm. And it's often explained in a really fuzzy way, like the quantumness just magically evaporates. But what's really happening in this model is that the phase information, the vapor nature, the coherence, it's not disappearing, it's just spreading out and getting tangled up with the environment.
Oh, okay.
The system becomes quantum with respect to a larger system.
Yeah.
The chair and the air in the room are now one big entangled quantum system.
So the weirdness gets diluted until we can't see it anymore in just the chair itself. It's like putting a single drop of red dye in the ocean.
That is the perfect analogy. The red is still there, technically. The ocean is now infinitesimally more red than it was before, but good luck ever seeing it or gathering it back into a drop.
The red is the quantum coherence. It's been spread so thin across the entire ocean of the environment that it's effectively gone from our perspective.
You've got it.
Okay, so the ghost has become a brick. The dye is in the ocean. Now we can finally get to the main event. Section 3, quantum uncondensation, the concept itself.
Right, and here is the central provocative question of the whole paper. If a droplet of water forms on my glass, I can boil it back into steam. We do it in our kitchens every single day. Can we do the same thing to a quantum event?
I have to stop you there, because the phrase uncondensing reality just sounds like we're drifting out of physics and into magic or time travel. We're literally talking about taking a broken egg and unbreaking it. Are we actually suggesting this is physically possible, or is this just a neat trick you can do on a chalkboard with equations?
It feels like magic, doesn't it? I mean, every instinct screams that it's impossible, but Nemoten is adamant that this is not magic, it's mechanics. It's just very, very, very hard mechanics.
But my common sense is just, it's going haywire. If I drop my coffee mug, it shatters into 100 pieces. The laws of physics don't let me just unshatter it.
Okay, but see, that's the twist. The fundamental laws of physics actually do let you unshatter it. That's the provocation here.
Right.
The deep laws of Motion-Newton's laws, Schrödinger's equation, they are perfectly time symmetric. They work backward just as well as they work forward. If you could capture the exact position and reverse the exact velocity of every single shard of glass, every molecule of air that was displaced, every sound wave, the mug would reassemble itself and fly right back up into your hand.
So why doesn't it ever happen? Why has no one ever seen that?
It's not because the universe forbids it. It's because you can't pay the price.
The price? What price?
The price in energy, the price in control, the price in complexity. And that is what this paper is all about. Uncondensation is not pretending the event didn't happen. It is a physical act of expending enormous resources to undo the conditions that made that droplet stable in the first place.
So practically speaking, what are the requirements? If I actually wanted to try and turn a brick back into a ghost, what's on the checklist?
You need 2 things. First, the easy part, relatively speaking. You have to protect it from new noise. You have to isolate it perfectly so that nothing new bumps into it and creates a fresh record while you're trying to erase the old ones.
Okay. Total isolation, put it in a perfect vacuum, shield it from everything.
Yeah.
I get that.
But the second requirement, that's the monster. You must undo the record.
You have to erase the footprint, every last bit of it.
Completely. As long as the universe contains even one physical record of which outcome happened, As long as there's a single scattered photon or one displaced atom out there that says the particle went left, then interference cannot return. The system cannot go back to being a probability wave of left and right.
So you're saying if there's even one witness, one photon floating around somewhere in the cosmos that knows where the particle is, you're stuck. You can't go back.
That's it. If the universe knows, the droplet stays a droplet. To make it vapor again, you have to find and essentially lobotomize the universe's memory of that specific event.
That brings up a fascinating point about the concept of irreversibility. We usually think of it as a fundamental law of physics, like a cosmic speed limit. Thou shalt not unbreak the egg.
Right, like it's a hard stop, a rule.
Yeah.
But Neymotin argues it's not a law that says SOP, it's more of a statement about lost access. It isn't forbidden by quantum mechanics to reverse an event. It's just constrained by how far the record of that event has managed to spread.
So it's not illegal in the eyes of physics. It's just a logistical nightmare of cosmic proportions.
That is the perfect way to freeze it, and it's the perfect segue into Section 4, the 3 regimes of uncondensation.
Yes. I loved this part of the paper. It takes this impossibly abstract idea and makes it so tangible. The difficulty of reversing reality is broken down into 3 categories, and it's all based on something he calls the record radius.
Exactly. The record radius is just a simple, elegant concept. It's the volume of the environment that now holds the information. How far has the splash from the event traveled? How big is the crime scene?
Let's start with the first one, regime 1, the possible. He calls this the tiny droplet.
Right. So in this scenario, the record that's been created is either incredibly weak or the droplet is just barely beginning to form. It hasn't really stabilized yet.
The analogy he uses is the bead on the window. I thought this was great.
It is. Imagine a bead of condensation just starting to nucleate on a cold pane of glass. It's microscopic. It's fragile. If you just gently warm the glass right at that moment, it vanishes. It evaporates right back into the surrounding vapor before it ever really sets as a proper droplet.
So it never truly became a stable, undeniable fact. It was a fact in the making that got interrupted. What does that look like in the quantum world?
In a lab, this looks like what we call partial measurements. Maybe the interaction process starts, an atom begins to interact with a detector, but you interrupt it before a stable, durable record can form.
Is it something that's actually been done? Or is it still just a thought experiment?
Oh, absolutely. This is real, and it's the heart and soul of the famous quantum eraser experiments.
I have heard of these, but they always melt my brain. Can you walk us through a simple version of it?
I'll try. So you set up a classic experiment where a particle can take one of 2 paths to get to a screen, path A or path B.
The famous double-slit experiment.
Exactly. Left to its own devices, it acts like a wave, a vapor. It takes both paths at once and creates an interference pattern on the screen.
A stripy pattern.
Now, if you put a detector at one of the slits to see which path did it take, boom. It acts like a particle, a droplet. It picks one path, and the interference pattern vanishes.
The wave collapses because we looked. The old story.
The old story. But here's the erasure part. What if you design the experiment so that you can find out which path it took, but then you erase that information after the particle has already passed the slits, but before its record has had time to spread out to the rest of the lab?
So you let the universe write the note, but then you burn the note before anyone else can read it.
That's a great way to put it. And when you do that, the interference pattern comes back.
Whoa, that feels like it violates causality.
Yeah.
You're changing the past.
It feels like it, but you're not.
Yeah.
You're just showing that as long as the record is contained and erasable, the system's vapor-like nature can be restored. As long as there is no permanent record anywhere in the universe saying it went left, the universe has to act as if it could have gone right too.
So interference is really just the physical evidence that the universe hasn't made up its mind yet.
It's the signature of possibility. And as long as we can successfully erase the record of the choice, the possibilities return.
And the key factor here, in regime 1, is that the record radius is tiny. We still have complete control over the environment that holds the information. We haven't let the secret out of the box.
Exactly. Another example he gives is something called reversible dephasing.
This one made me think of a group of runners on a track.
Yes, that's a perfect way to visualize it. Imagine a dozen runners starting a race, all lined up perfectly at the starting line. That perfect line is coherence. They're all in phase. Then the starting gun goes off. They all start running, but they're all at slightly different speeds. After a lap, they're spread out all over the track.
So if you just glance at the track, the group is gone. It just looks like a random scattering of individual runners.
Right. The coherence is lost, the signal has decayed, but, and here's the key, have you actually lost the information? No. If you had a magic whistle and you blew it, and every runner instantly turned around and ran backward at the exact same speed they were running forward.
They would all arrive back at the starting line at the exact same moment, back in their perfect line.
Exactly. You haven't lost the runners, they've just dispersed in a predictable way. You can refocus the signal, you can gather the vapor again, because you still hold the master key to how it's spread out.
Okay, so that's regime 1. Difficult, but possible in a lab. We can do that. Now, let's ramp up the difficulty. Regime 2. The hard. The contained record.
Okay, so now we're dealing with a genuine measurement. A stable outcome exists. A fact has been written into the universe. A droplet has fully formed. But the key difference is that this droplet and its immediate record are contained within a box that we can, in theory, completely control.
So the toothpaste is all the way out of the tube now, but both the toothpaste and the tube are sealed inside a Ziploc bag.
That is a very vivid and accurate analogy, yes. The record exists, it's real. So to uncondense this, we can't just gently warm it. We have to actively fight it. We have to do work. We have to shove the toothpaste back in the tube.
What are the strategies here? What does that work look like?
One of the biggest strategies is redundancy. This is a massive field in quantum computing. You don't store your fragile quantum information in just one particle. You distribute it, you encode it across many physical carriers, many atoms or photons.
It's like making a backup. Saving your file on 3 different hard drives.
It's a bit more subtle than that. It's more like a hologram. You know how if you break a hologram plate, each little piece still contains the entire image, just a bit fuzzier?
Right.
It's like that. The information is stored non-locally. So if one part of your system gets accidentally measured or bumped by the environment, if one part of the record gets damaged, you can use the information stored in the whole structure to detect and correct that error. You're actively engineering coherence to fight against the natural tendency to condense.
It's like a self-healing quantum state.
It is. It's active error correction. Now, another approach, which is even more radical, is dynamical reversal.
This is the one that sounds like straight up rewinding the tape.
That's literally what it is. You try to precisely reverse the microscopic evolution of every single particle involved in the event.
Yeah.
You let the system evolve forward for a certain amount of time, and then you hit it with, say, a carefully timed magnetic pulse that effectively makes all the interactions run backward.
But that sounds completely impossible, the level of control you'd need.
In this regime, it's not impossible. It's just very, very, very hard. The catch, the reason this is so difficult, is that even the tiniest imperfections get amplified exponentially.
Why is that?
It's chaos theory, the butterfly effect. If you want to reverse the paths of a billion billiard balls on a table, but you miss reversing the angle of just one of them by a millionth of a degree, that tiny error will compound and cascade. By the time you expect them all to be back in the starting rack, they'll be scattered all over the place.
So it works on a chalkboard, but in the real world, you need absolute perfection.
You need a level of precision that is almost godlike, but we can do it with very small, very controlled systems.
And the third strategy he mentions for this regime is shrinking the environment.
Yes. This is why so much of quantum research happens at temperatures just a fraction of a degree above absolute zero. If you isolate your system in a high vacuum and cool it down so much that the atoms are barely moving,
then there are fewer things for it to bump into.
Exactly. There are fewer places for records to hide. You are intentionally starving the system of an environment it can write its memoirs in. If there are fewer stray atoms and photons flying around, there are fewer records that you have to worry about erasing.
So what's the final verdict on regime 2?
Not impossible, but astronomically expensive, both in terms of energy and control. It's an engineering challenge of the highest order. It is a question of cost, precision, and error correction.
Okay, and now we get to the scary part, the part that explains why we can't unbreak eggs or walk through walls. Regime 3, the effectively impossible, the escaped record.
This is everyday life. This is the macroscopic world we all live in every second of every day.
The analogy here shifts from the tiny bead on the window to something much, much grander. He compares it to the city.
Yes, imagine trying to reconstruct a single specific droplet of water from steam that has now dispersed and spread across an entire city like London or New York.
That just feels hopeless on its face.
And physically what's happened? The splash from the event has rippled out uncontrollably. Photons have bounced off the object and are now scattering into deep space at the speed of light. Air molecules have collided with it, then they've collided with billions of other molecules, sharing that little nudge of momentum like a rumor spreading through a crowd. Heat has flowed from the object into the table it's sitting on. Memories of the object have formed in our brains, or its image has been captured on a security camera and stored on a hard drive.
The record isn't in a box anymore. The record is the world.
The record is everywhere. And this leads to what is, I think, the single best description of Schrödinger's cat I have ever heard.
Okay, I have to admit, usually when the cat comes up in these conversations, I kind of roll my eyes. It feels like such a cliche. The cat is alive and dead at the same time until the scientist opens the box. Blah, blah, blah.
Right. It's always presented as this mystical, spooky, zombie cat state of being.
But Nemotin, he cuts right through all that mysticism. He says the cat is not some magical creature in limbo. He says it is a factory for environmental records.
A factory! Just let that image sink in for a minute. A factory.
Help me see it. What do you mean, why is the cat a factory?
Okay, think about a living cat. It's a complex, warm-blooded biological machine. Its body temperature is, what, around 101 degrees Fahrenheit?
Right, it's warm.
It is a blazing lighthouse of infrared radiation. It is constantly blasting the inside walls of that box with billions upon billions of photons every nanosecond. Those photons are screaming a message into the environment. I am here. I am warm. I am alive.
So in the infrared spectrum, the cat is just glowing.
To the universe, it's as bright as the sun. And that's just heat. It's also breathing. Every single breath it takes pushes moles of air molecules around, creating tiny wind currents and pressure waves inside the box. It's shifting its weight, which sends vibrations through the floor of the box. Its heart is beating.
So the idea that the universe doesn't know if the cat is alive or dead until a box is opened is just wrong.
It's completely wrong, according to this model. There is no superposition for the cat because the record radius of its state is expanding at the speed of light. The secret isn't contained in the box. It's constantly leaking out through the walls in the form of heat and gravity and vibration. A dead cat is cold. A living cat is hot. The box gets warm. That's the record.
So to uncondense the can, to try and turn it back into a 50-50 probability of being alive or dead.
You would have to catch every single infrared photon that it ever emitted and put it back. You'd have to reverse the trajectory of every air molecule it ever breathes on. You'd have to undo the gravitational pull it exerted. You'd have to find the scientists who put the cat in there and wipe their memory.
And here's the real kicker, I guess. You'd have to do all of that without making any new records of your own while you're gathering up the old ones.
Precisely. It's like trying to sweep a dirt floor perfectly clean. Every single time you move the broom, you kick up more dust. You cannot interact with the universe to erase records without simultaneously creating new ones.
So when Nemotin uses the word impossible here, he's being very specific.
He is. He means physically unattainable, not metaphysically forbidden. There is no sign on the wall of the universe that says you cannot put the cat back into superposition. But the scale of the complexity, the number of particles you'd have to control, is so astronomically large that the probability of success is, for all practical purposes, 0.
This brings us right back to that central concept of the record radius. It really is the organizing idea for the whole paper, isn't it?
It's the yardstick for reality. Small radius, possible to reverse, huge radius, effectively impossible.
And this leads to a major philosophical shift that the paper is arguing for. We talked earlier about observation, that old idea that a human consciousness looking at something is what makes it real.
Right. The consciousness causes collapse theory, which has always been a bit problematic.
Well, if observation was the cause of reality, then logically, unobservation, me just closing my eyes or turning my back, should reverse it.
Which is obviously absurd. The tree in the forest doesn't vanish and turn back into a probability wave when you blink.
Exactly. So Nemotin just replaces the whole messy concept. He says, since record creation is the cause of reality becoming definite, then record erasure is what's required for the reversal. It takes the human out of the equation.
And this brings us to the quote that I highlighted like 3 times in my notes. It's so important. He says, "The universe does not care whether a human looked. It cares whether an outcome became copyable."
Copyable. That's the key word there. Can the universe make a copy of this event? Can the information spread? If the answer is yes, then it's real.
It completely shifts the focus from a subjective conscious act to an objective mechanical one. It's cleaner, it's more consistent, and it explains why the moon is still there even when no one on Earth is looking at it, because the moon is constantly writing indelible records of itself via its gravitational field and the sunlight it reflects.
Okay, so if we accept all of this, that reality is just an accumulation of physical records. What does this tell us about time? This is section 6, and it's where we connect all this quantum stuff to the big question of the arrow of time.
This is the grand finale of the argument. Because, as we said, we know the fundamental quantum equations are time-symmetric. They work just as well backward as forward. There is no arrow in the deep-down math.
Right. If I showed you a video of two atoms bouncing off each other, and then I played it in reverse, you wouldn't be able to tell which was the original. It still looks like perfectly valid physics.
Exactly. So why does time in our world feel so relentlessly like a one-way street? Why can't we unspill the milk? Why can't we unsay a cruel word?
The usual answer is thermodynamics. Entropy always increases. Disorder always wins.
True. But Nemotin asks us to look at thermodynamics through this new lens of information. Think about condensation again, the forward direction in time. It's a process that takes a delicate, fragile quantum state and entangles it with the entire world. Information spreads out.
And as we've established, spreading is easy.
It's more than easy. It happens for free. The environment wants to interact. Nature is an unstoppable gossip. It can't wait to tell everyone the secret of which path the particle took. Heat naturally spreads from hot to cold. Gradients naturally flatten. This is the path of least resistance.
Okay, and uncondensation, the backward direction.
That requires gathering all that dispersed information and concentrating it back into one place. This actively resists the natural flow of the universe.
He uses the analogy of unmixing coffee and cream.
It's perfect, isn't it? Pouring the cream into the coffee, easy. Gravity and diffusion do all the work for you. The cream spreads out, the information of its location becomes dispersed.
But getting the cream back out of the coffee.
You'd need a centrifuge, you'd need complex chemical separators, you'd have to put in a massive amount of energy and do a huge amount of work. You have to fight the system every step of the way.
So the conclusion he draws about time is just, it's fascinating. Irreversibility feels absolute, not because of some fundamental law, but because of an overwhelming statistical preference.
The universe overwhelmingly prefers processes that spread information and create records. So the arrow of time, the reason yesterday is different from tomorrow, isn't some separate, deep mystery of physics. It is the macroscopic shadow of record creation.
Time points forward, simply because records accumulate.
That's the bumper sticker for the whole theory. We are always moving toward a future that is more recorded, more condensed than the past was. We are building a mountain of these physical records, and climbing back down that mountain is astronomically harder than falling up it.
That is actually kind of a heavy thought when you stop and think about it. Our past isn't gone, it's just fossilized. We're buried in our own records.
We are. We are constantly fossilizing the quantum world of possibilities into the classical world of history, moment by moment. Every breath you take writes a record into the thermal and kinetic state of this room. That is, for all intents and purposes, indelible.
So let's try to bring this all home. We've gone from vapor to droplets, we've classified the difficulty of turning those droplets back into vapor, and we've realized that Schrödinger's cat is basically a furry, purring heat radiator.
We have definitely covered a lot of ground.
To close the loop on the central idea, QC, or quantum condensation, explains how possibilities become facts. QUC, quantum uncondensation, explains the cosmic price tag for trying to undo those facts.
And the most important takeaway is that they form a loop, but the loop is profoundly asymmetric.
Forward is effortless. Nature does it on autopilot. It's the default setting.
Backward is expensive. It requires impossible levels of control, energy, and precision.
It's just easier to make a mess than it is to clean it up, but on a universal scale.
Fundamentally, yes. That's a pretty good summary of the second law of thermodynamics seen through this lens.
This has been an absolutely incredible deep dive. It really does change how I look at sitting here in this chair. I feel like I'm actively condensing into the room.
You are. You are writing the story of your existence into the physical structure of the universe right now.
I want to leave our listeners with the final provocative thought from Nemotin's text. It's definitely something to mull over tonight while you're lying in bed, radiating infrared photons at your ceiling and creating records.
It's a thought that really stays with you. He concludes by writing, reality becomes definite because the universe records, and it stays definite because those records are written into the material world. The loop exists. It is real, but it does not turn freely.
It does not turn freely. I love that. A perfect final image. Thank you so much for walking us through this. This has been amazing.
My pleasure. It was a lot of fun.
And to you, the listener, thanks for being part of our condensation process with us. Keep asking these big questions, keep creating records, The good kind, hopefully, and we will see you on the next deep dive.